So now we are going to start the presentation by the Fabless companies. Originally we planned that we will, allot 10 minutes each to, these Fabless startups, but we are actually running really late, 1 hour. So what probably we'll do, we'll prompt. Okay, so we'll try to finish, each presentation in about 7 minutes. And if there are some questions, we can probably take it up. So we'll still try to finish in 10 minutes, but along with Q&A. So you're all set, right? We'll probably just wait for a minute or two, or shall we just start? Probably we'll just start. So you're ready to project. Yeah. So probably we'll start with the morphing machines. So I would like to invite Dr. Chandan Haldar to give the presentation on his products and offering. Thank you.
Good afternoon, ladies and gentlemen. My name is Chandan Haldar. I'm the CEO of Morphing Machine. And since we have a little bit shortage of time, in one slide, this is what we do. And in the next 4 or 5 minutes, my goal is to make you understand what this really means and where we are with respect to this product or this offering, and why we think this is going to be an important, interesting thing in the next few years. So the first question to answer is, why do we need such a thing at all? And if you look at the situation in the marketplace today, what's happening is that we all know which applications are demanding massively parallel processing. It's very clear that there is a whole bunch of applications where that is the way to go, and people are trying to go in that direction. The only problem is that the massively parallel processor accelerators market is basically stuck with one option today. And that one option is the GPGPU. So the entire market essentially is right now a virtual monopoly of one single company, a company that came back from the brink of a pretty bad situation and logged $8 billion yesterday. So the problem is this. The problem is GPUs are excellent machines. I mean, there is no doubt about that. They're very good in certain things, and they're not so good in certain other things. And the point is that shortcoming, which the kind of things that they're not able to do very well, is not, a design defect or an oversight or a matter of improvement. It is an architectural deficiency, and the issue is how those deficiencies can be overcome by alternative architectures, and how we are trying to do that. So what's the downside of this for applications? The downside is that since there is no other option in the market, so if anybody wants to do massively parallel processing today, and the only commercially available, easily available option is a single platform, then you can rest assured that anybody who needs to do that will coerce all problems into that format. And that's exactly what is happening today. So the GPU architectures are nice 20th century architectures, and in that architecture, the one thing that you can do very well is what is known as SIMD, which is a single instruction multiple data kind of computation, where the exact same computation you want to repeat for numerous numbers of the different pieces of data. And unfortunately, not all problems are SIMD problems in terms of their solution structure and the algorithm structure. But since that's the only available solution, therefore all problems are being forcibly cast into that format and being solved using that one platform which is available. So we believe that we need a new massively parallel processor platform, which is different. I mean, it's not just an alternative in the sense of another SIMD product, but it is architecturally different, and which has several other advantages as well with respect to high performance computing of all sorts. So this is what redefined looks like. And these are the 5 key defining attributes of the redefined architecture. This is our flagship architecture and the processor name as well. And unfortunately, in this few minutes, we'll not be able to go through a lot of details of each of these things, but I'll try to get you the crux of the matter. This is massively parallel because it's of the same scale of parallelism as the largest GPUs you get in the market today. So basically, we're addressing the exact same segment in terms of how much scaling you would be able to do and how massively parallel is it. The customizability comes from the ability to incorporate custom function units, for acceleration of atomic computation kernels, which are very low level, small computations that you do repeatedly in certain set of applications and so on. For those things, we can actually add custom function units into the compute fabric, and therefore those computations get done in silicon speed. This is something obviously not possible for commercial off-the-shelf products like a GPU. The scalability part I already mentioned. The reconfigurability you'll see by means of some pictures later, or if you're kind enough to step out to the demonstration setup for our FPGA emulation outside. So there are two key aspects in which GPGPUs falter, despite their merits in several other ways. One is the SIMD restriction, which is that they don't do MIMD very well. When the instructions diverge, then all the threads become sequential, and there is a huge problem. So the performance basically plummets if you switch to a different type of problem. And like I mentioned before, not all problems can be fit into the SIMD mode. So this is a major handicap. The other major handicap is the power consumption, because we all know what happens to the GPU power. So the amount of power that those chips burn inside, is just phenomenal and mind-boggling, and that's not a good thing. Because 2 years ago, we were making a presentation about Redefine in Paris, and the main theme there was about power consumption, environmental impact, etc. So when you have a single SoC burning 200 watts, there's a serious problem. Because ICT worldwide today is running something close to 2 petawatt hours of power, electricity every year. And this is only increasing very rapidly. This is not a good scenario. We are contributing right now, the ICT sector alone is contributing more than 10% of the total energy consumption of mankind. So these are things which are getting very serious now, because we all know the state of the planet and what all is happening on that front. So so these are the two serious problems that we are thinking about when we think of the limitations of GPUs and what one could do as an alternative. One is how to overcome the SIMD challenge, and the other is how to bring the power consumption to a reasonable scale. And once again, the power consumption of GPUs is not a design oversight, or it's not a matter of more effort. It is the intrinsic limitation of a 20th century architecture which has come down to us today, so many years down the line. So an architectural change is necessary to solve both of these problems. It's not a matter of a better design. So what are the key benefits of the redefined architecture before I tell you more about how it happens? The resource needs of all concurrently executing acceleration kernels, which we are trying to run on the parallel fabric, are allotted dynamically configured virtual cores. We are not going to be able to understand this within the next few minutes, but please take my word for it. The resources that every concurrently executing kernel requires is exactly the resource it will get from the runtime system at the time of execution of that kernel. And this is heterogeneous. So depending on the size of the kernel, it's going to require different amounts of resources. It will get it from it. This architecture maximizes not only SIMD performance, but also MIMD performance, because we don't deal with control flow in the way that the GPU, the SIMD architectures do. This is a data flow driven architecture where each subtask executes on its own as soon as the input data is available. And they exchange data between them by communicating messages over a network on chip, which is a message passing architecture, not a shared memory architecture. And therefore, MIMD type of problems, which drastically slow down the execution on the GPUs, have no impact whatsoever on this architecture. If you have the time to see the demo, you'll see some examples of that. Custom hardware acceleration, I think I already mentioned. We have the ability to allow at design time to add custom function units to basically siliconize atomic kernels which need to be executed many times in many different applications. The other thing that one can do is we have reconfigurable function units which can be software programmed dynamically at runtime under the control of the kernel that's being launched on the packages. So imagine a very simple example if you want to visualize this. Suppose I would like to compute a particular arithmetic expression again and again in a particular application. This is not something for which I would like to make a specific piece of hardware in my redefined SoC, because it's a general purpose SoC will do many different things. So the reconfigurable function units allows me to compose an arithmetic computation tree at runtime dynamically on the reconfigurable function unit. And thereafter, that particular expression evaluation will happen at silicon speed, which means the fastest possible under the circumstances. will not talk about hardware fault tolerance much here, but that's a very important feature. It's NOC-based architecture. There is a tremendous capability and architectural support in the platform to allow for faulty nodes or certain compute cores beginning to malfunction, memory malfunctions in the distributed memory, etc. So there's a whole bunch of things that support that aspect. And finally, the power management capability is way superior to any platform that we are ever having. And this happens because of the way the compiler drives this platform to do the computations and the amount of information that the compiler can actually generate at compile time based on static data flow analysis and the instructions that a particular kernel is going to execute. And based on that, how the power management metadata for the runtime can be generated by the compiler. Here is a straight comparison with the GPGPU architectures. This is the shared memory architecture, redefined as a distributed memory architecture. The memory also is distributed along with the processing cores over the entire network on chip. The parallel computing happens on GPGPUs by in a program-specified manner, driven basically by control flow, just like synchronizing or running in synchrony a large number of threads, all doing the same thing at the same time. Whereas in case of redefine, the parallel computing happens by programmer specification, all right, but also by compiler assistance at the compile time to extract and expose additional concurrencies which are present in the program but not explicitly specified by the programmer. And then the computation is entirely data flow driven. This is not data flow in the 1980s sense, but this is data flow in a macro data flow sense, which is a kind of reinvention of the data flow architecture that we used to see 25 years ago. So these are the fundamental differences between the architectures that you are seeing in front of you. There is no custom hardware acceleration possible for GPUs because they are commercial off-the-shelf chips. But and also the design doesn't permit any custom hardware. They already have what they have, and that's about it. Redefine permits two types of customizations. I already mentioned these to you earlier, so I'll skip over that. Performance-wise, while the GPUs can only do well data parallel assembly algorithms, Redefine can do both. So we sacrifice very little when you want to do assembly computation in contrast to in comparison with GPUs, and we outshine GPUs right from start in terms of MIMD algorithms, where the different threads of execution that is happening at the same time, the concurrent threads, are all divergent. Does this make sense to you or not? As a simple example, in a computation, it's not always a straight line. There are always conditionals. Without conditionals, one cannot have non-trivial programs. Now, in the case of SIMD computations, where you want to do the same computation on 1,000 different pieces of data at the same time, if one of those 1,000 threads take the then clause rather than the if clause, and the other 999 take the if clause, these computations will happen sequentially. So this is one of the major architectural bottlenecks of the GPU design, and that's exactly what we overcome in this architecture. The power management I mentioned as well earlier. So what's the status of this product? The FPGA prototype you can see outside when you step out. We are ready for backend design. Our goal is to produce a standalone SoC, which means it will also have the host or the control processor on board. And the redefined compute fabric will be an accelerator at the back end of that processor. So all the peripherals and GPIOs, etc., will be handled by the front-end processor. So this will be possible to use in two different ways. It will be possible to use as a standalone SoC to run a complete system, like in various kinds of embedded systems if required, depending on what level of parallelism and concurrency we require, the size of the fabric. It can also be used as add-on accelerators like PCI cards, etc., in larger systems where we are trying to build chassis-based systems. Applications, we actually do a lot. I mean, this is a general purpose massively parallel processing accelerator. It, of course, will do AI and machine learning algorithms. But unlike the Google TPU, for example, which is for all practical purposes a TensorFlow accelerator, it doesn't do anything else. It's an excellent machine, good effort, nice design. The TPU2 is even better, but it is a TensorFlow accelerator, period. It doesn't do anything else. Whereas the GPGPUs actually do a lot of things, and of course they pay the price for it because they're assembly machines. So we do a lot of things, but we don't suffer from the limitations of the TPUs, like being dedicated to doing only machine learning and nothing else. We can actually do everything that the GPU does. The reactive control systems is specifically mentioned here because our first global early adopter customer is from that domain. They are avionics customers. They run these kind of systems to control aircraft engines and stuff like that. So it's very important for them, for us to implement those kind of algorithms. We do those pretty well. We also run a whole bunch of numerical algorithms from linear algebra and other things, basically the whole gamut of scientific computing and HPC applications. The revenue figure, well, while it is important not to take it too literally, but just consider the fact that right now, the market, which is more than $10 billion sheerly in terms of the MPP accelerators alone, is currently in a virtual monopoly with one company which logged $8 billion revenue last year. Some part of it came from gaming systems, which kids used to play nice games, and the other came from the back-end data centers, the AI cloud, and such uses. So yeah, don't take this number too literally. We go from day to day. So with all due respect to the beautiful long-term strategies, etc., that we do need, at this moment we live from day to day. So my job is to take 0.1% of the existing market that I saw last year in the LPP accelerators market next year. If we can do that when we have the first SOC, I think our first step would have been taken. We also have some other products, and most of these IPs came about essentially as appendages of the redefined architecture, because I told you we support custom function units. So we had to build a redefined crypto core, basically a very high performance AES crypto engine for a customer. Unfortunately, it didn't see the light of day in the market. But so for that kind of usage, what we do is we develop this point IP, right? So this is the AES accelerator IP, and we can attach that as a custom function unit into the compute fabric with each compute processor in each compute core. So the result is that let us imagine I have 1,000 core redefined. Basically, I have 1,000 core crypto accelerator engine which nobody in the universe can match at this point. So that's the kind of impact that we expect to have with all this point type. All of these point IPs were basically designed and implemented to plug into Redefine. It so happens we can also sell them independently. We haven't made serious attempt to sell them at this moment. The NOC router is the core of the Redefine network on chip, and that has become a point IP by itself. So all these are FPGA validated and ready for backend design. If there's any user, any of you would be interested, we'll be very happy to talk to you about. The revenue impact of this, I don't really know. I just put some number over there. Quick little bits about the company. We were launched from IESA and incorporated quite some time ago. We are an old company. We have, like Parag said before, we have been here, we survived. We are a pre-investment company. We have no external investment other than some IESA involvement right in the beginning, which is not worth writing home about. We have survived. We have survived on small little bits of revenue here and there, and some very supportive customers since the last 4 years. And we are still here. We would have the SOC out hopefully within the next year. The first couple of years went basically going from research to product mode and figuring out what 20 years of research at IISc could translate into in terms of bringing out the complete product in the market. Make some early prototypes, experiments. Professor Nandi is the founder of the company. He's sitting here in the audience somewhere. The next few years was about bringing out the base redefined platform and building up the first compiler which could compile the target code for that and create some of the other point silicon IPs that you saw before. Then came the critical time. 2013 to 2017 till last year, is a lot of things happened to us. First of all, our customer walked in. That's the Safran Group, which is the world's second largest avionics group. These guys provide aircraft engines to very serious things like the Rafale aircraft. Unfortunately, we could not get onto their offset bandwagon. So we are basically on their research engagements. But they are outstanding customers. We're really happy with them. They have been very supportive. They have been with us for 4 years, and they are really waiting and pushing us now for getting the SOC out. So this is where we stand right now, trying to get the SOC out to satisfy their interest. We have a single small office in right here in Bangalore, near IISc, and all our development engineering, etc., happen over there. We are very few people. We are really a small company. That's why it took us 12 years to develop this. So you can imagine. We have had a few little milestones here and there. Early on in 2011, Gartner featured us in the Cool Vendor Semiconductor report. Out of the blue, it was very, very interesting at that time. The Safran Group became our early valued customer in 2014, and they have been with us since then. Because for them, the time is not very long. For them, the certification time for a new processor is like 5 years. So 3-4 years for them is nothing. We demonstrated that's the first public appearance of Redefine at MIT in 2016. We showed an image processing demonstration. It was very widely appreciated, looked at by people who are considered worldwide the fathers of data flow computing and high performance computing in multiple ways. People like Jack Dennis, Professor Arvind, etc. Very encouraging for us. In the same year, we featured as the top 50 finalists in the Hello Tomorrow Summit, which is a very important event in Europe. We did not get the bumper prize at the end, but then fantastic experience and exposure. And most recently, the NSM is showing a lot of interest. We don't know what will come out of that at the end because Delhi's ways are mysterious, but we hope some really good things will happen. So if that works out, we'll be in very good shape on that front. This is our team. My colleague, Dr. Anjani Narayan, is the CTO of the company. She is right here with me, and also Professor Nandi, who is the founder. And now we call him the honorary chief scientist. And there's a whole bunch of guys. So our model is a little different. We continue to stay tagged on with IESA in a very close way because we work so much together. All the publications that we do together. When it comes to some very cutting edge research that needs to be solved in a particular way, the research teams at IISc look at it more closely. When it comes to productionizing that, bringing it onto the platform, incorporating it into the redefined SoC, upcoming SoC, that part is done more in the morphing machine. So it's a little hodgepodge kind of scenario, but it works very well for us. Top 3 priority actions, of course, we have to make the prototype SoC first. This is the top action right now. And we also have to make a small little board which can host that. It's not that that is the end product, but this is a critical requirement so that we can throw it in the hands of customers and potential customers and other users. There has been a lot of demand from Indian academic community and research communities. So a lot of people are interested in getting this so-called GPU equivalent, which has been designed and built in India. So that's very interesting for us. Second, of course, we have to start going on the application software stack, which we have not been able to do so far with so little bandwidth. And the plan is to start with, not with TensorFlow, but with things like Chainer or Caffe, and then go to TensorFlow, because TensorFlow, nobody will come to us for TensorFlow because there is TPU from Google. But if we could have a fantastic accelerator for Chainer, for example, if we could beat the Intel processor performance on that, hands down, that would be a good start. So we would be starting with that and then going to other issues. Numerical computations, we are doing very well already. And then the third and most important action will be to convert Safran into a regular customer. I mean, Safran, of course, is one of the world's most desirable customers for something like this. But they're a user organization. So we need to first make this a commercial product, and then they will be the, probably the world's largest user. But we still need to convert them in any case, and then go after the next customers. And the first segment that we'll be looking at will be the AI cloud data centers, because like I said, in the last 3-4 years, worldwide, all the AI cloud data centers are filled with GPUs. If we could take just one floor out of those thousands of floors of buildings that are filled with those chips, I think we will have a start. So the first SoC we try to build will be a 1000 core redefined with various other specifications. We expect to run it around 1 GHz to start with, and it will have an onboard RISC-V 64-bit multi-core as the host and control processor. The board this is not our board. I mean, it's just an artistic impression using the BeagleBone image, but that's the idea. So people get a small-handed little thing which they can play with, write programs, compile, and execute. This is the table that we needed to fill up for this presentation, and of course we need a lot of things because we are a small company, we have very little resource, and we hope that we will be able to raise investment very soon, and then some of these things will become simpler. Money, yes, that's a big yes. All the others, yes, very good to have. For example, foundry access, certainly we require marketing support. It will be really good to have because we are not experienced in that very much. We are lucky that a very good customer walked in and worked with us for so many years without any questions, but sooner or later that luck will run out. So I think we need some support on the marketing front very urgently. So other than that, I think everything else that we are talking about, in a way, can be had if we had the money. So that sort of something that I wanted to say. So that's pretty much it. I think I'm done. This is the concluding side. Thank you very much for listening. If you have any questions, I'll be happy to answer. You want the honest answer? There was nothing. So, see, in 2000, early 2000, that's when all this incubation business was becoming big time, right? So the government got some ideas in their mind. They wanted to seed something, give some money to the IESA and some of the IITs, etc. The institutes had no clue what they wanted to do or what they had to do with that money. Nobody knew anything. So Professor Nandi is here. He can tell you that story later in more detail. But basically what happened was that at IISc, people looked around. Nobody was standing up to say, yes, I'll take that money and do something. So he happens to be the guy who stood up and said, okay, let me start something because we have been doing parallel processing research for 25 years. We better have something which is worth taking to the world. Right? So that's really how the company started. And of course, we have all been, at one time or another, we have been in parallel and distributed computing research ourselves, long time ago. I mean, I did a little parallel computing research and then I shifted to AI algorithms in those days. This is a long time ago. Then I left, I went to the industry, and finally, when we all came together, we all had this common thread of parallel computing. Ranjani worked for a great deal in data flow computing in those days with Professor Arvind at MIT and other people. And lot of things were making a big comeback. Three things are making a big comeback right now. I'm sorry, I'm taking a lot of time, so please excuse me. One thing we know already, this thing, so-called machine learning, deep learning hype that's being generated today. Neural networks were a big hit in the mid-80s when we were still in our research days. And they didn't take off very well because the silicon capability was not there. Right? We couldn't compute fast enough to be able to do large networks and do the iterations that are necessary. So today, when the silicon capability arose, then immediately the whole algorithm made a big comeback. And now all that you are hearing about deep learning, etc., is nothing but the neural networks we used to do in those days in a slightly quick form here and there. We are doing a lot of brute force approach now, taking big networks, applying massive amount of training data, and hoping for the best. So deep learning has its own issues. So neural networks made a big comeback. In general, AI is making a big comeback. Parallel computing made a big comeback because of silicon capability. So the third thing that is also making a big comeback is this data flow driven computing. Because data flow, the way it was being attempted at that time, was fine grained, typically tagged architectures which didn't work very well because it required silicon support which was not available. And as such, the architecture was too fine grained. So today we are trying to bring back those ideas with a different avatar and working very well. So data flow is working magically at the macro level, where you, instead of doing taggings at instruction level, when you start thinking of tasks and the relationships in terms of data exchange, suddenly things start looking so fantastic. So to answer your question, I mean, we really started with some very vague ideas in our mind. Then it sort of crystallized to making a highly parallel accelerator. And then in between that, the AI and machine learning, deep learning, this whole wave happened right in front of our eyes while we were still developing our stuff. So then we further twisted to the idea that we need to make a standalone integrated processor because we can serve the edge very well. See, most of the low-end AI or the early AI, pre-processing AI is going to happen at the edge. It's not going to happen at the core. Core will only transact packets and be done with it. So for every small thing, you don't want to go back to the cloud data center. It's too expensive to do that. And if you want to do it at the edge, then you need processors over there which can do that. And I think we are going to fulfill a very interesting niche over there. So given the fact that we are able to do it very power efficiently and with a orthogonal architecture that overcomes several limitations that the GPUs have. So that really is how we started doing this.
So I hope any more questions we'll take it offline, sir. So
Thank you very much.
May I now call upon Ravi from MMRFIC. Just a minute. Haldar sir.
Thank you, Mr. Chandan. Sorry about that. We have a small gift there which we would like to showcase it to you. Uh, Anybody? JC, request you to kindly come and give this to Chandan. Thank you, Chandan. Thank you, JC. Thank you.
Good afternoon, everybody. My name is Ravi Vijayaraghavan. I represent MMRFIC Technology. It's an acronym. Uh, Before I start my presentation, I would like to first appreciate the efforts taken by all here in engaging this Fabless ecosystem, Conclave, and for working hard tirelessly for that to create an impact in the country. So MMRFIC is a company that is focusing on millimeter wave RF products with the expertise ranging from RF design experience uh, based on the effect that we are the founder directors were all alumnus of Texas Instruments and each come with a varied experience in RF design, signal processing, power management, and RF layout. And so far, we have in the company have 5 patents filed and one granted recently. So the core team from MFIC are Sarvana Kumar, Dr. Ganeshan is here with us. He is the CTO. Sarvana Kumar is the CEO, and myself, Ravi, and the other two senior leaders in the company. Along with the five, we are a total size of 15 people as of today. So the uniqueness that MRFIC brings in is obviously its expertise in millimeter wave RF and the full chip ecosystem. The kind of diversified team that we have got and the experience that we have got, the capabilities of the company expands itself in multiple technologies, GaN, GAS, SiGe, CMOS, and LTCC. And over the last couple of years, the company has proven itself in its silicon and board level performances and the capability to also provide these solutions in small form factor RF millimeter wave products. And given the breadth of the expertise in DSP and power management, MMRFIC becomes the company that can provide end-to-end solution. And where I mean end-to-end being from all the way from antenna to bits for processing in the backend. So that is one of the USP of the of our company. And add to it to be able to take such solutions and demonstrate to end customers where we integrate the machine learning and radar signal processing algorithms to be able to differentiate and show applications and use cases that can be productized for the customers. So we have a dedicated team working on it as well. So this has been our journey. We started off in 2014 where we started with just 3 engineers in analog and RF expertise, and today with 15 engineers we have expanded to our office in Hyderabad, have our machine learning expertise and MMIC expertise added to the team, and productized our first MMIC solution to the customer, and along the way filed multiple patents, as I mentioned, and recently we were granted the first patent in the US patent office. And this year we are extending our portfolio by developing a couple of novel products in the millimeter wave regime. To touch a little bit on the product portfolio, this may not be the complete list, and we'd be happy to discuss in detail about what we are doing and the other products that we are focusing on. If there's any questions, the first product is for the W-band radar, which we are sampling to select customers, and it is targeted applications are in the automotive and industrial space. The second one is the proprietary beamformer across different frequency bands in the millimeter wave, and primarily focused for the communications, both 5G and satellite, as well as for radar use cases. And this is a proprietary scheme, and it is under development for demonstration to select customers. The IP development roadmap for us was one of the IP development we did was for the RFID in 5.8 gigahertz, and this was demonstrated in silicon, and that was also delivered to production. So basically, this is an IP that we have sold to a customer after demonstrating the performance in silicon. And this is a single chip solution, is an SoC where it executes the whole RFID performance. So this gives a sample of where we touch upon where it's a product is diversified, single chip, and customized solutions, as well as proprietary in its nature, to show the breadth of the development we have had. So what we are looking at as priority is having done our sample the first silicon and wanting to expand that portfolio beyond to multiple millimeter wave front-end applications, and to be able to differentiate ourselves in the market. So that is one area that we are focusing on. The other one is using the sensor technologies to take it to IoT and provide end-to-end solution. These are there are some applications that we are already addressing there. The third one is the machine learning that we have been working for the last 2 years, I would say, which we demonstrated in one of the radar symposiums as well. And we are continuing to engage in that to be able to provide data fusion solutions for the end customers with the hardware that we are developing in-house. Support requirements as a startup, as a bootstrap company, tools and test packaging in millimeter wave radar, where we are touching all the way up to W band, is going to be a challenge, and that's one area where we are looking to engage and see where we can address, because of the cost of the test, the packaging capabilities that is limited within the country, and the tools that are much needed to make sure that we can successfully fabricate and succeed in delivering the solution. Apart from that, given our technology focuses, we are also looking at how we can expand our market. Currently, our market focus is to a limited set of customers that we can engage and be able to address their address their requirements. At the same time, how we can expand this market beyond where we are addressing, and to be able to grow our portfolio and expand our business. So that is another area. And obviously, on the funding side, we are a bootstrap for the last 4 years, and we continue to operate that way. So we have had a mix of being able to fund ourselves with our IP capabilities to engage and develop our products, and to expand our IPs and to be able to make the products more viable. We need to probably ramp our with the funding story as well. But we are looking at ways to grow that, but that is a continual process. Yeah, and that's all I have. I think I'm probably the shortest one. Are there any questions? We have customers that varied both in the public sector side as well as on the commercial side. So it is both within India and offshore as well. We have a couple of engagements in India tied with a couple of fab. One is TSMC, the other one is in Malaysia, the third one is in IHP in Germany. So we pretty much fabricate offshore and bring and import our designs back to India for demonstrating the solutions.
Thank you. May I call Hemant to? I would now like to invite Sumit Mathur, CEO, Cyril Systems.
Good afternoon. I'm going to talk a little bit about Cyril Systems. So we started operations in 2013. We were spun off from a company called Cosmic Circuits. We were the IC division of a company called Cosmic Circuits, and in 2013 we started as Cyril Systems. We focus on analog mixed signal ICs, so power management ICs and active capacitive stylus ICs is what we work on. We have 6 patents. We have a analog mixed signal team of about 35, and in the last 5 years we have shipped about 20 million units, mostly in the stylus domain, but also in power and MEMS microphone ICs. So in terms of the product lines, there are really 2 domains which we are focusing on, power management ICs and active capacitive stylus ICs. So power management ICs, we have several of them, but I mean, I've listed the product names here, but really what this means is, what we are focusing on is power management ICs for portable and wearable electronics. We have a IP base of solutions based on which we develop solutions, either custom, solutions or standard solutions. So the standard solutions are mostly targeted on the battery management and fuel gauging, that type of application, whereas for the system PMICs are done alongside a customer. So that's the power management domain. One of the power management ICs is actually currently being used in a 3D camera module. So the key differentiation there is size, and I'll talk about it a little bit later. On the active capacitive stylus IC, we have 2 ICs there. One IC which has been in mass production for several years now. It was used in the Microsoft Surface Pro 3 and the Surface Pro 4 styli. And we are now building a new solution. We just taped it out. Silicon is expected this month. This is a stylus IC for a new protocol, as well as the enhanced Microsoft protocol. So this is a multi-protocol stylus IC. We expect 3 to 5 million per year revenue from this. We are already doing good business on the first one, the CCA 1001. We are shipping several hundred units per month, and we have got 2 large customers, but of late about 4 or 5 new customers, mostly in Taiwan and China. So in the active capacitive stylus domain, so far we have been focused on IC. We are looking at moving towards a full reference solution or a system or a module, and here we are building. So we have the ASIC and the electronic expertise, but we don't have the mechanical solution. A pen has a lot of mechanical components with it. So the mechanical components of the pen is something that we are working on, and we are trying to build a complete solution so as we can demo it to OEMs. So these are the main product areas, but we also have a MEMS microphone solution. So we have 2 products which are mass production ready. One is a digital microphone, and other is digital microphone with I2S interface, which is good for smart speakers. So directly the microphone can interface to the processor without any intermediate chip. So yeah, so in terms of the power management solution, we have got several ICs, but the common theme across them is the solution size. So we are targeting the least number of external components and trying to keep the solution size as small as possible. Uh, Of course, as in power management domain, the efficiency of the buck converter is crucial, and the quiescent current of the buck converter is very is crucial. So we have we have different kind of buck converters, but we have one buck converter which has quiescent current of as low as 500 nanoampere. So the efficiency even at 0.1 milliampere is more than 90%. So the other key differentiation in our product space is the integration. So we can integrate all the functions that are needed in a system from power management point of view. One of our chips shown here has a 2 ampere switching charger, an intelligent power path, several DC-DC converters, backlight boost, USB boost, fuel gauge, all of that in one chip. And the other differentiation, especially for the wearable space, is that the PMIC is an extremely can be in an extremely low power sleep state and can put the entire system to sleep and count time or wake on an event like an accelerometer shake or something. So keeps the system in a very low power state and then wakes up quickly and wakes up the rest of the system when needed. So so that's the power management space, and then on the stylus space, the new chip that we have done is compatible to multiple protocols. We are seeing that more and more tablet and two-in-ones are adopting the stylus, and of late we are seeing some design-ins in the mobile space as well. So because Samsung Note is popular, so several Android phones are adding small form factor pens. And our IC's unique capability is that it's extremely low power. So you can make a supercap powered stylus, and it lasts several hours on a supercap. So that's the yeah, these are the two product domains and the kind of products that we have built there. In terms of the key priorities for the company right now, we are focusing on getting more market access to our power management ICs. We are working on partnership and funding for this right now, and we're working with certain partners for that. So on the active capacitor stylus, of course, we just taped out the chip, and we now really need to get it into design and get it into pens of several leading OEMs whom we are right now working with. And then, as I mentioned, that on the stylus space, we want to go beyond the IC. We want to look at building a complete solution so that our customers can adopt the solution faster. Right now, we only supply the IC, and the cycle time to get to market for the end customer becomes longer. But if we have a complete reference solution, that will be faster. So that's what we are working on. Yeah. So in terms of funding, yeah. So as I said, we are working with some partners on funding and partnership. But certainly, we are open to more partners, and also we are in the current context right now. We are certainly looking for funding for some of the critical R&D, especially the stylus, and but the biggest need that we have is reaching out to customers, and that's really what we are working on.
Questions?
What kind of customers?
So it depends on the product space. So in the stylus, our customers, the end product is used by OEMs like HP, Dell, Asus, etc. Right? But our customer is an ODM in China who makes the pen. So that's for the stylus world. So these are ODMs in Taiwan and China, which make the pen, and we supply the IC to them. And for PMIC, we have some of the customers are like SoC companies, alongside whom we design the PMIC, and we supply the PMIC either to them or to their customer. And for MEMS microphone, our customers are integrators of the microphone module. So we supply only the ASIC. The microphone is made by integrators in China, and they buy the sensor from somebody and ASIC from us, and make the module. So this is the set of customers that we have. So mostly in Asia, mostly in China and Taiwan.
The products as well are displayed outside.
Yeah. So we have a demo of some of the products, or most of the products outside, and we will be happy to talk about them in more detail.
Thank you, sir. So, may I now call upon Dr. Venu from Manjeera Systems.
So we couldn't make the slides in the required format. Sorry for that, but we have a slide deck that I'm showing here. And I will start from where Dr. Halder concluded. That is the same mission, or mission of freeing the world of abuse. So this is about high performance computing. Our IP is for high performance computing. There are many applications which were already mentioned for this. Just to get the story clear, let me start with one example which everybody talks about now, artificial intelligence. And artificial intelligence is applicable in so many areas. Like all these things are given here. But what artificial intelligence means, whether it be machine learning or some other technique, what it means is huge data, and then smart data models to extract information out of it, and then the ability to process that huge data using complex models. That is where the processors come from, and that is where you need high performance computing. And it's already said many times that there are no suitable processors available for really to take this huge problem. Okay. So Universal Multifunction Accelerator, UMA, is our IP and our product. And this UMA is central to various products offered by us. And this tries to solve this problem of high performance computing. And it's a fundamentally new architecture. In short, 100x better than the best that is available currently in the market. And we have already silicon validated this IP. And here is a chip and a development board with our IP. Okay. So let me sort of quickly state where the gap is, what is the problem, and how we approach to solve this. Dr. Halder has already nicely summarized various architectures and weaknesses in that. And of course, when you talk about high performance computing, it's mostly GPUs. Okay. And in any case, let me consider all the available existing architectures. And when you are talking about high performance computing, you are looking at 4 metrics. That is performance, power consumption, programmability, and silicon area. You want the performance to be as high as possible, power consumption to be as low as possible, programmability should be as high as possible, and the size of the chip to be as small as possible. That means money you want to spend on chipping out the chip should be as small as possible. Okay. And these are the gaps. I will not go through them once again. But the red areas are the gaps in the existing architectures, starting from CPUs, GPUs, even when you talk about custom ASIC or hardware accelerators. We address this problem with a fundamentally new approach, and the computing methodology itself is different compared to all these architectures. We call them middle stratum operations based computing, and a data path architecture that supports middle stratum operation. That is Universal Multifunction Accelerator, UMA. So with this, again, we have a lot of data. I don't want to go deep into the technical aspects. We have benchmarked, and more importantly, we have our customers who have validated this. So with that, I will not try to prove any more, but the conclusion is that we have exactly the type of behavior as you need. As you need, this is in the first column, whatever is needed, this is what we are able to get. Okay, so 100x value proposition is 100x better performance per square millimeter area on the chip, per square milliwatt power you consume, and per dollar you spend in fabricating the chip. That's the value proposition. Where is this UMA useful? UMA can accelerate either DSP algorithms or something like artificial intelligence algorithms, or things like vision processing algorithms. What are the technologies that get benefited with this sort of acceleration? All these technologies are the ones which get benefited. And what are the verticals where these technologies are used? These are all the outer ring is the verticals where these technologies are used. So in principle, EMA is useful in all those verticals, industry verticals. Okay, here is quickly some data. Again, as I mentioned, whenever you talk about high performance computing, it's mostly GPUs. So you see comparison with GPUs. These are the benchmark data collected at our end, and then many of them are validated at the customer end. So it is like quickly 6x better performance and 10x lower power consumption, and then 25x smaller area. Overall, it's a huge differentiator. About our customers, Intel is our customer. We have been our first customer for FPGA. Actually, the first revenues came from IESA, and here in Intel, our IP is used on FPGA for multiple purposes. Currently, we are doing a project for AI-based server acceleration, wherein our IP sits on Area 10, Statics 10 FPGA, and connected to Intel Core for accelerating artificial intelligence algorithm-based applications. And the application now is being targeted is deep speech. This has essentially for server acceleration, and we know the strategy of Intel for server acceleration. That is why other FPGAs are used, and we are able to provide a solution on FPGAs for this. And this is slowly building into a big relation with Intel. And together we are planning to conduct some demos to the Intel customers and so on. So a business group from Intel is involved in that. Though it started with I2R group, now PSG group is involved, and there is a very high potential for revenues in this project. And the other one is the chip that we have built is for Indian navigation IRNSS applications. This is a baseband processor for IRNSS. As we know, Government of India is trying to make this, as it was mentioned in the morning, mandatory. Once the local manufacturers are available for the chips, we have already manufactured this, and we have an order from ISRO for delivering the NAVIC receivers based on the chip, and this is the baseband board for that NAVIC receiver. Together with an RF board, this becomes a complete receiver. And this is a huge potential even before this is made mandatory in India. As such, it is a huge potential because Ministry of Electronics and Information Technology, MeitY, is soon going to come up with a proposal to build about 1.6 million chips of the same size, and we already have built the prototype of this chip. This is built at 28 nanometer node of TSMC. Okay, we have few other customers. I will not go into the details, and we have fairly decent revenue projections in this year, and we may be breaking even in this year. We are a good start. Our revenue model is through FPGA, providing FPGA-based solution, as well as providing EMI IP for ASIC, and then chip manufacturing, and particularly for Indian market. So we have already started this, and hence we will definitely be benefited if there is a fab available within India. When we suffer many of the problems which were mentioned in the morning, because we have to get them manufactured somewhere and get them back here, and few iterations and so on. And again, this is a huge revenue potential area. And there are other customers as well. Yeah, I guess I covered all the items in the revenue model. Sorry. Okay, so the market potential for high performance computing, it's about $50 billion. That's what it said. These are all the various verticals where high performance computing is needed, and our IP is seamlessly scalable, so it can on one hand be used for something like edge computing in IoT, where you want a very small silicon and low power consumption, all the way to server acceleration, where you really want huge computing power. And it's very easy to scale our IP from one end of the spectrum to the other end. So we can address all these areas, but of course we are focusing on these two main projects I have mentioned, namely doing a baseband chip for Indian applications, and then server acceleration with Intel. So we are a 5-year-old startup, and we are about 24 full-time employees now. We are, as I said, we are already silicon validated our IP. Okay, so what's our goal? This is an area where, this is a forum where we can really dream big, and so we do, and this is what we want to be. We want to be a high performance computing processor coming out of India, but with a global impact. Okay, and we need funds for that, and we need. I'm sorry, I don't have that format, but definitely tools, and we need to have presence globally, and then we need to have a dynamic team which can, market the IP. We need to have all these things, but again, if we have funds, most of them will come, as it was mentioned in the morning. Okay, so this is it. Thank you for your attention. I hope I managed it in the time. You can take time.
Maybe we could take answers offline, sir, at your demo booth.
Sure.
Yeah? So may I call upon Devashish Datta, sir, to do the honors for Dr. Venu. May I call Dr. Reddy from Terminus Circuits?
Good afternoon, everybody. I'm Shankar Reddy from Terminus Circuits. I'm founder of the company, and the company started in 2010, which is into interface IPs. To give brief about it, earlier we had started with wireless battery charger, which is the data transfer as well as power transfer wirelessly. That's the time when we approached some of the VCs as well as government organizations to fund for it. The question I got is, where is the equivalent product in the market? I'm not able to answer to that question because there was no such. And that's the time, if I had completed that one, now when people are talking about IoT was not kind even by that time. If that product is available now, where data and power can be transferred, or all wireless network connectivity has happened without any customer lights. And then and mostly the sensors which are being used, 95% of this battery will go off without using it. Because, for example, smoke sensor, when you use it, I don't know, I never seen any smoke sensor being used any time. It may be once in 10 years, one sensor may be used. And most of the batteries that will go bad or go out of life just by consuming power without being used. So whenever it is needed, we can charge it and take the data and then discharge it or disconnect it. That was the proposal that was that point in time. Unfortunately, it didn't play out. Then immediately we moved to interface IPs, which are going to be, that point in time, I think people are talking about abroad in US and China, US, China, Japan, about high performance computing. And that's where we started the high performance computing related products, not from the point of system building, but from the point of interface IPs that are being built, which are cornerstones for any IP HPC to be started. This small introduction, I'll just Parag, I don't know where you are, but anyway, I take your point now. If you see it in the slide, the team is put in the middle or in the lower bottom of the slide. Probably products are being put in the field name. I'll take your point, I'll change it. So this team is having 3 doctorates, 2 of them from IESA. One is myself and another Javed. And also we are supported by the marketing person, Open Control, who has 16 years of experience in these areas. And we started with the, as I said, interface products like PCI Gen 4, USB 3.1, multi-standard SerDes, MIPI, M5, Gear 4. If you see all of them, PCI Gen 4 standards which are matured and 1.0 version has come up in October 7th of 2017. But we started this in 2013-14 timeframe. To parallelly with standards when being evolved, we started working on that. And USB 3.1 is the recent one. And Raja can tell about the USB 3.1, which is you may be evaluating right now from here. Multi-standard service it all depends on the MIPI M5 Gear 4 is the one which is upcoming in the market. You see, all the time we are catching up or going ahead along with the standards that are being evolved. The idea is when the standards comes up, we should be able to take it up and then say that immediately can give our solutions to the end customer. And achievements wise, we have done 6 silicon tape outs, starting from 65 nanometer TSMC to 28 nanometer TSMC, Global Foundry, and Samsung. All these 6 tape outs have 11 products in those tape outs, which are basically either PCI generations or USB generations or multi-standard cell generations. MIPI is the recent one, there are no MIPI in that. And we have licensed a complete ASIC solution to a customer who is into HPC system. Now it's good to know that everybody is talking about HPC, supercomputer, and all that, artificial intelligence, deep learning, machine learning, all these things. But these things which have been done by us in 2013-14 time frame, where we have given a complete ASIC solution to the European customer as a part of European Union project, deep project, in which they were trying to build exascale computing that point in time. Deep is nothing but exascale computing, platform building for exascale computing. So what they did is they have filtered out 10 companies across Europe, and have taken 13 companies out of the 10 countries and given the task for each of the products or each of the companies about which part of the deep project they can work on. We are fortunate enough to Avian ASIC Solutions, one of such companies, which they have built a system based on complete of our ASIC solution as 1 terabyte per second throughput. And they have done at the system level the latency, which is much less than 1 microsecond, that is 650 nanoseconds latency. And for any HPC system, that's a killing combination where throughput can be high and the latency can be less. And also we are awarded the most innovative product of the year by IESA in 2013 as well as recently in 2017. I just stuck to the format that is given by IESA. So these are the 4 products, the portfolio what we have. One is, as I said in earlier case of PCI, and then USB, and then multi-lane SerDes, and then BP5. We can talk about the applications that these things can be used from the point of high performance computing or cloud computing, deep learning, artificial intelligence, and all those stuff. And also we recently had a tie-up with one of the leading upcoming RISC-V processor based platform builders. So you may be knowing C5 is the one which we have tied up. The interest of theirs in our company is from the point of the solution which we already provided on similar lines way back in 2013-14, but that time the processor is Intel-based processor. Intel-based process where PCI is the controller is there in process, and then interface is given by us. And now RISC-V is coming up. So along with RISC-V, the PCI controller can be done. It can be used from the point of chip communication as well as across the board communication. So I don't know whether I have time to go through this in detail each one by one. But as I said, the applications can be plenty from the point of HPC interface and then network on chip. That is going to be critical from the point of chip-to-chip communication or board-to-board communications, where throughput and latency that matters a lot. And maybe the one recently we started, we are going to take out in September end, and it's C++ process, where we can use multimedia content, cameras, and etc. And another story I just wanted to, not story, I just wanted to tell here is set-top box, when we are not having any infrastructure in India, that has gone to somebody else where entire set-top box business is gone. But it's not till late from the point of HPC, where we can build from the point of hardware onwards, where the company like Turner Circuit, which is already have given the program or complete ASIC solution to similar HPC computing system builders way back in. So it's not that okay. If you keep on losing time, even a national supercomputing machine that started may end up taking complete solutions from somewhere else and build the board level integration of the supercomputers. So maybe you can have the ecosystem built by that time. And fortunately, we already started long back on this, where we can effectively enter. We can communicate with the people and then also give the solutions. As I said, the format says what is the problem statement. Supercomputing or exascale computing system is need of massive parallel processing, cost rate, and cycles, and then also low latency. So the PCI is actually working on the connectivity part of it at the high data rates, where not in the point of the standards coming up. And at present PCI has taken 4+ years to come out from PCI Gen 3 to Gen 4. Seeing the need and necessity of the current scenarios, PCI also ramped up, and then they want to come out with 32 Gbps data rate, PCI Gen 5 by June next year. Just they started last year, and then in 2 years they want to finalize the 1.0 version of the specs. Whereas they had taken for the previous one for 4 years plus. So that shows how much is in demand from the host side connectivity of these systems or high-end systems. As I said, PCI is going to be a cornerstone from the point of network function, from the point of SSD drives, and also from the point of chip-to-chip applications. So that's the main core of that, and that is going to be a key solution for all these high-performance computing systems. And when you're talking about the board-to-board communication, PCI Gen 4 with the need of longer channels. Now there is repeaters or retimers are deployed in the recent report what we did last month, July 11th. We had done a retimer as well as PCI Gen 4 with the latest specs, 1.2 previous specs in our recent report. So we do have a solution for retimer also where long cable connectivity is needed in the server application side. I'm getting signal that time. I make it on. So the game-changing solution, as I said, the critical part of it is throughput and latency, which we are already having a solution, which we already have given the solution to the end customer here. And the markets, as I said, this is the market which is going to catch up, and then everybody is going to be talking about it. And the recent trend is instead of going for the regular available process, the RISC-V processor is one which is going to add to the HPC systems, and which RISC-V processor along with the native PCI solution, we can give all the necessary solutions from the point of storage, network on chip, as well as chip-to-chip communication. And fortunately, Indian government has identified National Supercomputing Mission, which is going on at different levels now. There we can have contribution if it is needed. And the infrastructure from the point of Digital India programs, and then also from the point of defense and aerospace, even from the point of single board computing, our solution can be used. Because it talks about the peripherals connected, it talks about the chip-to-chip connectivity, and also to make entire solution at the single board itself. Top three priorities. Top three priorities from the point of products. SSD for solid state drives, and as of now, I think in the market, PCI Gen 2 based one are available plenty, and Gen 3 based are available at server level. Gen 4 is not come at from the point of market adoption. As you see, these final specs are completed only last October. So we are getting a lot of traction from the point of Gen 4 based SSD computers. And the set-top box, anyway, it is gone business as far as India concerned, but still there is a scope that it can be built in India, Indian-based SSD. Network on chip is having its own importance from the point of HPC or cloud computing or artificial intelligence. Support requirements. Probably the EDA team, which is maybe sitting around, may not like this, but EDA tool cost can be optimized if it can be put on a, support can come out with a plan where EDA license can be pulled, and then need basis people can access it. Financial assistance can be done through ESDM. Earlier it was thought it can be done. I think not based on the submission of reports and all that. It can be done from invoice. Okay, if I'm doing an MPW, directly that invoice can go to ESDM. Maybe Sapal can help us in that. And then whatever concessions we can get can be directly given to the foundry itself. And ecosystem is a big worry from the point of Indian ecosystem, from the point of packaging, and then also even for making the board level solutions. System prototyping, we need support. And fund support, as of now, we are doing IPs on our own. But in case if you want to go for the product-based ones like SSDs and MOCs, which larger systems can be built, definitely we need the financial muscle as well as organizational restructure as part of it. Marketing support from the point of Indian, the market that is available for the products in India as well as the product. Mentoring maybe required from the point of finance and business and training. With this, I just conclude this. Any questions I can take after, or we move on more questions?
One question, sir. Any?
Okay.
May I request Vikram Nave to do the honors?
Right.